prize fellow at Newcastle University, and I work with Tom Penfold, one of our organisers. So you'll probably all know Tom. We're basically working on machine learning for X-ray spectroscopy, trying to develop some fast and affordable models to predict X-ray spectra. But today I'm just going to take a break from the usual bits because I'm chairing the talks. So yeah, I hope everyone's seated comfortably, popcorn ready. It's a really great lineup of talks today. I think it'll be a pretty good introduction to some of the research that's going on in the community. So yeah, I hope you enjoy it. I know I will. And kicking off the first session is Sam Hall from the University of Warwick. And Sam's going to be telling us a bit about simulating core level spectroscopy to reveal something about chemical bonding at the metal organic interfaces. So if you want to take it away, Sam.
Thank you for the introduction. I'd like to thank the organisers for allowing me the opportunity to present my work to you today. So obviously, like I said, I work in simulating core level spectroscopy. And so won't hear everybody probably knows about core level spectroscopy and what it can provide information-wise. It gives us information about the electronic structure of systems, and that can give us information of various different things like absorption geometry, the electronic structure itself. But one thing what can happen is, especially here, if you start using molecules like this porphine ring here, if you start looking at NEXA spectra of conjugated aromatic systems, that's where spectra can start to get a bit convoluted in your analysis of it, and you can get overlapping features and peaks, and you want to be able to see and break those down, because mainly here, as you would see in this example here, you can kind of see 3 peaks here, but what do they correspond to? Is they for one level, or is this an overlapping feature? Especially this one here, you can't, it's quite harder to see. And then even more so, what can complicate the spectra even more is then when we absorb these molecules onto metal surfaces. So as seen here, you can see this onto a silver surface. If you were to compare the two, you'd normally say there is not really much interaction going on, because the spectra comparing the two stay relatively the same. But then when we look at it on the copper surface, we can see it changes quite a lot. And obviously this is where you would say the molecule is heavily interacting with the surface. But the problem is you cannot really now see any features. You just see, you can maybe point out where you would think them to be, but it's not very clear. And what we want to be able to do is look at these kind of systems and try and help using our simulations to break down what is actually going on, and look at this as they go. We want to be able to break it down into various different effects. And so one of the effects is these initial state effects, where we look at the individual carbon atoms in the molecule and see how they contribute to the spectra. And then there's also final state effects. So actually looking at molecular orbitals themselves. So looking at the orbitals of the molecule and see how that affects the spectra, or what is causing these in the spectra. So then to be able to do this, then we need to get a system of various different systems that we can look at, and that has various different interaction strengths, because this is what we want to see here. We've just got 2 different systems, but we want to have a range of them and see if we can find something that happens where they have a different interaction effects, not just a strong and a weak. So what we're looking at these 2 molecules, naphthalene and azulene, and we want to see if we can get them into various metal organic interaction strengths. And so with this, what we can look at is of these 2 molecules themselves, as there are structural isomers of each other individually themselves, they will have a different reactivity of them. And then also we then look at them on these 3 different metal surfaces. So we have a low reactive metal in silver, a high reactive metal in platinum, and a middle one of copper. And so then what we can do is we can, if we absorb them onto all of the metals, we then get a total of 6 systems. And these systems as well, a benefit for these is they've been studied by some collaborators in very good experiments. They've looked at the absorption geometry, energetics, and also the NEXAs themselves as well, which helps us to compare our our simulations with, so we can look at them before, which isn't the main focus here, is comparing them to them. But obviously, if you want to look at how our simulations compare to the experiment themselves, you can look at these papers here. Or I could talk to you another point, or organize a meeting with me later during this conference, and I can talk to you about it. But mainly then what we want to look at is the change in interaction strength. So here we have the calculated values of our systems. So first we can look at the absorption energy. And as we go across the system here, we're increasing the reactivity. And we can see, obviously, as we expect, the absorption energy is increasing as we're going along from the low reactive metal to the high reactive metal and in between the two molecules themselves. And also then the inverse trend can be seen in the absorption height. The absorption height is now decreasing as we go across. But then if you were to look more closely at these values themselves, you can kind of split them into three different groups. So we can split them, these three here, into what we will just say is the weakest out of all of the three. Then we have this middle system here of azurine on copper, and then this is the intermediate one, and then both our platinum systems are very strong. And also what can be seen here as well visually, you can see obviously the absorption height, but also the deformation in the molecule itself. So again, here the first three, they remain relatively planar, as you would expect. These are planar molecules. But then as we then increase from the intermediate to the stronger, we can see deformation is starting to clearly come into the molecule itself. So then what we want to do then is, now we have our systems, we then want to then study the next aspect there and see how it changes as the reactivity increases and what is the cause of that. But then obviously first to do that, we need to calculate it. And how do we calculate our spectra? So obviously we use CASTEP, which is a pseudopotential, plane wave pseudopotential basis set. And we use, if you're interested in these few values here. But the main thing I want to highlight of what we do is, obviously, being a pseudopotential code, it doesn't explicitly state the core electrons themselves. So to get around this, there is, to include the core hole in our calculations, we create a pseudopotential which has this core hole included. And then what we can do is we can calculate the XPS spectra, and we use this using the delta self-consistent field method. So this is here, we include a 4-core hole in the molecule itself. And then we do this for each individual atom in the molecule. And then to get the binding energy, we take the difference in between the total energies of the excited state and the ground state. So if you see here, you would then need n plus 1 calculations for how many atoms there are. So obviously in the azurine and naphthalene case, there are 10 carbon atoms. So you need 10 excited calculations and then 1 ground state calculations to compare them all. And then for our next staffs, we use this delta IP corrected transition potential method. And then what this one then is, we use a half core hole instead of a 4-core, full core hole. And so this then in CASTEP, we use the LNES module, which this is just basically a band structure calculation, which helps us to converge the unoccupied states. And again, we do this for each individual atom. And then to then get our next spectra, we then take the energies that we get for all the different transitions, which in our method as well, we can do them in one calculation. We don't have to model each individual transition. This is what the transition potential method allows us to do. So then we shift the individual energies that we get for individual atoms by the XPS binding energies, and then we sum them all up, and then we apply some broadening, and then that's how we get our next spectra. And then due to inherent difficult problems with using a pseudopotential method and periodic boundary conditions, we then have to convert our spectra to match the experimental scale if you want to compare to experiment. So then here, this is then what we can get our simulations. So first thing we did, we calculated just the gas phase. So just the molecule itself without the interaction of the metal surface, just to get a baseline of what the spectra looks like. So first then what we can show then is what we can look and see from the spectra. So obviously with naphthalene and azurine in the XPS here, we can see obviously a shoulder coming through at lower energy. And then this can then be transferred and seen over in the next house where we have a lower leading edge. And then comparing the two NEXAS spectra themselves as well, we can see that for azulene, we have this broad first peak, where in naphthalene, we can see more individual peaks. So then what we will be able to do then is using our simulations is now break these down and what more information can we now gather because of our simulations. So the first thing what we can do is the initial state contributions, as I mentioned in the beginning. So this allows us to break down the molecule into the individual atoms and see where the spectra comes from. So obviously here for naphthalene, you can see that the individual atoms are relatively quite close together, and this is where we get one peak. But then for azulene, the individual energies themselves are much more spread out. And here then we can actually see what is actually causing this lower energy shoulder. And this is mainly from these two carbons here in more of this 5-membered ring. So we can see that this lower edge is from the smaller 5-membered ring. And then also we can now do this also for the NEXAS itself. So this is then just for the NEXAS for the naphthalene. And here again, we can see now a breakdown of what actually carbon atoms are included in the, I'm sorry, I think the neighbour's drilling outside. We can see that this first peak here is contributions from this atom and partly of this there. So basically we can see and break down what is actually causing more spectra. But then also what I mentioned is the final state contributions. So here what we do is we project the molecular orbitals onto the NEXAS spectra. So here we're showing both the LUMO +1 and +2 for both naphthalene and azulene. And again, what we can see is that we can see clearly that each of these first 3 peaks that we can see is the main contributions is from each LUMO orbital. But then for azulene, we can see that actually this broader first peak is actually from a contribution from the LUMO and the LUMO +1. And so then we can see then more of actually what is going on. And this is something that you might thought this could just been one peak if you just had the spectra itself. So then what we want to do is then look at the interaction of the metal surfaces. And we've now got our baseline of what we think it should look like without in the interaction. Now we'll see how the interaction changes. So we first start looking at the weakest interaction. So it's three systems up here. So up here, we've got all of our 3 spectra, and we've shown them here for 3 different incident angles. So we can simulate at various different incident angles as well. And we can see going down from all of them that there is not really much change between the spectra, only from a slight broadening compared to the gas phase. We can still see clearly quite the individual features in each of them. You can also see that the dichroism remains intact. So as we go from the 25 to 53 into the 90 degrees, obviously this is looking at obviously the differences between the sigma and pi orbitals. We can see that as we go down, obviously if we get to 90 degrees, we lose the intensity of this first peak, and which is seen in all of these cases. Then what we can also look at is we can project the molecular orbital density of states. So obviously this here in the black line is our density of states, and then in these different colors here, obviously starting off with blue is from a HOMO and going lighter is going down, and then our starkest red here is the LUMO, and as we go up, going lighter shades are going up. And obviously these have been scaled to easily view, to be seen a lot easier. And then down here, these lines represent the orbitals for the gas phase. So then between this, again, comparing the silver and the copper compared to the gas phase, we can see that there isn't really much change between the orbitals themselves. They're staying how there is in that. There isn't really any hybridization between the molecular orbitals. It's not really interacting with the metal that much. So then moving on, we can then first look at the intermediate interaction. So this then, if we're just looking at, which is this azulene on copper. So if we compare it now just to the azulene on silver, which I also didn't show you before, just showing you here, to compare with them with, as we go from the weak to the intermediate, we can see now some difference in the spectra itself. We can see that this first peak is now reducing in its intensity. And also, if you kind of look closely as well, the dichroism, you kind of lost the dichroism as well here. So on the 90 degrees spectra, we can now actually start to see some intensity in the 90 degrees. And now we want to see, like, break down what is the cause of this. And so looking at the MODOS that I showed before, we can actually now clearly see hybridization occurring. We can see this LUMO is now actually partially occupied. It's below the Fermi energy. And both all the molecules are smearing out. And then looking more into the molecular orbital projection, and we can see again, we can see the reasoning for this lower peak, this lower first peak is due to the contributions of these, the LUMO and the LUMO plus one have significantly reduced. Whereas the higher orbitals, they kind of stay the same. So these peaks here are kind of the same, but that the reduction is mainly due to this hybridization of these molecular orbitals. And then finally, we have our stronger interaction. This then is obviously for both platinum cases. And so here is what we simulating. So here are the two spectra of the two molecules. So in our system like this. And if we're looking at them individually, without any knowledge or knowing what was there, you couldn't really tell they're kind of indistinguishable from each other. Without knowing, you can't tell which one's azulene or which one's naphthalene. They kind of just both smeared out into this kind of mess, really. You can see individual peaks, but you can't really glean much information from it. And without knowing them, you can't really tell which one's which. So here with red, here is the naphthalene, and the blue here is the azulene. And obviously comparing this to the gas phase, as we can see, is very differently. You can see that the individual peaks have all gone and they're all smearing out. And we'll then try and figure out what is the cause of this. Is this due to hybridization between the molecules, or is it could be a reason for the deformation? Because as I pointed out earlier, there is now strong deformation in the molecule itself. Is that a cause for it? And it's what our method allows us to do, we can actually pinpoint this and see what is the main cause of it. So what we can do, we can calculate the deformed molecule spectra. So we take our system here and we just delete the metal surface, and then we do the same process before. We actually then just calculate the spectra of this deformed molecule. And yes, we can see that it does affect the spectra. It does change it compared to the gas phase. That is not the main reason what is causing this smeared out and the loss of these features. It shows this is more due to the hybridization of the metal, and that the spectra is actually more just showing the metallic states, and that's why they look so similar. And so then what we want to look at is then, can spectra alone determine the interaction strength? So obviously, if you were to just run these experiments themselves, you would basically get a range of spectra that looks kind of like this. You could compare them all together, and you could see them as we go through. We can see in the interaction strength as we're going down. We can see that the first peak intensity is going down. And normally, what would you highlight that to? Normally, you would highlight that to due to charge transfer. And as the interaction increases between them, the spectra smears out, and this is due to charge transfer. We lose intensity in this first peak. And so if we look at the charge transfer values, we can see that obviously for the weak interaction, there isn't. And we have some charge transfer in the intermediate case here, the azulene on copper. Then when we look at the values for the platinum cases, they are again 0. They show the same similar values as the weakest ones. And we understand this doesn't kind of make sense what's going on here. But then obviously this more is due to the Duncanson model, where obviously there is charge transfer. We are getting donation from the molecule into the metal, but then also we are then getting back donation from the metal back into the molecule, which overall gives a net charge transfer of 0. So then this is more just showing our breakdown of what's going on. So obviously, what I'd like to show then is obviously for our calculations, we can look at the spectra themselves and really find out that experimental data may not offer really a full picture of what you can get. You can certainly get information from it, but what we want to be able to show is actually what causes the changes in the spectra. So we want to look at the molecule. What I hope shown is that we can look at these interactions and see what causes it, and offer quite an in-depth analysis into the reasoning behind these changes. And through all these different methods here that I've highlighted here that I've shown you throughout this talk. And so then what we can do, we can kind of paint a picture of the chemical bonding of what is actually happening. And so then that's all left for me is to acknowledge these people here for helping with the funding and members of the Mara group who have helped me through my work. And I thank you for your attention. And if you have any questions, I will gladly answer them for you. Thank you.
Okay, cheers, Sam. It was a pretty interesting talk. We have got a few questions already in the question and answers, so I'll just read those out to you. The first question we have is about slide 6. If you could take us back there. Yes. The question is, how was the convolution for the NEXAFs obtained? Was it fitted to experimental values?
Yes. So obviously, in the papers that I mentioned for the spectra. So obviously the gas phase spectra, what they did, they ran the multi-layer spectra for that. And then we then take our spectra and we shift it to match the energy scale, because obviously the our energy scale, or the energies that we get out from the spectra, do not match due to problems of the method, the superpotential. And so we just add a shift to the spectra to match the experimental values for both for the XPS and both NEXAFs.
Okay, the second question we've got in the chat now is, do the work functions of the metals play a role in this, and do you account for it in your calculations?
Work functions. So no, we don't account for the work functions. So this is so this would be then if you were calculating an absolute spectrum. So if you were using what we've looked at, other methods which you can calculate the absolute values of the XPS, you then would have to take into consideration the work functions to compare to experiment. But obviously, due to the method that we use, because the energies that we get are considered off anyway, the work functions, we don't have to take that into consideration because we shift our spectra anyway, so we don't take into consideration the work function.
Okay, and just one quick question for me before you finish. So have you considered at all the effect of defects on the surfaces or uncoordinated sites and things like this? Is that something you've looked into or plan to? How that might affect the binding?
Sorry,
it's say, for example, missing atoms, uncoordinated sites on your surface. I assume you're treating this as like a perfect surface, effectively.
Yes, yeah.
Yeah, so in reality, that would be
this something we haven't looked at into any of those effects or anything like that. We haven't, but that could be something in the future to try and look into. I haven't really seen much information on that, so obviously that could be an interesting avenue in the future too.
Yeah, I just wonder whether it might sort of affect the method of binding or kind of the precise positions and things somewhat. But yeah, no, that's interesting. Thanks a lot. Okay, so if there's no other questions, thanks again, Sam, for the great talk, and we'll move on to the next one. Coming all the way from sunny California, from Stanford, we've got Cheng-Tai, who's from the Stanford Synchrotron radiation light source. He's going to be giving us a talk about two-dimensional electron system behaviors studied with RIXS by the look of it. So Cheng-Tai, if you want to take it away.
Okay, right. Thank you. Let me share the screen first. Okay. Okay, can you see the screen now?
Yeah, that looks good.
Okay, great. I'm gonna start. Thank you for having me today. I'm Cheng-Tai from SSRL. Today I'm going to present this RIXS study on aluminum oxide, titanium dioxide heterostructures. So first I will give a brief introduction on this newly discovered two-deck system, aluminum oxide, titanium dioxide. Then we will introduce the tool that we are using, the RIXS. So in particular, this titanium L3H RIXS. It can pop this titanium 3+ and the 4+ contributions, and also this DD excitation, D1 fluorescence. These are basically from 3+. And then it pops this low energy loss features, is the electron phonon coupling effect. So these are all related to the interface carrier two-deck of any kind of material, well, not really, from the titanium-based materials. So that's why we want to use this titanium LH RIXS. And at last, I will summarize our findings. And if we have time, actually, I can also share with you these future directions on this restarting of this system. So before coming to the science part, I would like to thank all our collaborators for accomplishing this nice work. So Professor De-Kyung Jo, who I believe is also in this conference, so he introduced this interesting system to me and also initialized this RIXS study. So I would like to thank him and also Professor Park's group that provided this high quality heterostructure sample for our study. And all these experiments were carried out in the advanced Lightsource in Dr. E.D. Zhuang's QRIXS end station. So two-dimensional electron system refers to electrons that are confined in this very narrow depths, but it's free to move in the in-plane direction. This concept 2DEC has been widely used in semiconductor industry. In 2005, 2006, scientists, they discovered a new system, new 2DEC system in LLSTO heterostructure. This was a very important discovery to the field of transition metal oxide. These oxides can be synthesized using PLD or MBE, meaning that we can change the combination of oxide heterostructure. We can control it, and by doing that, we can control the 2DEC. However, using this PLD and MBE, there's some limitation. It has this limitation of size and the production rate due to this technical difficulty. This is where our system pops out. So our collaborator using this ALD, this industrial equipment to deposit the same thing, and they find this system, aluminum oxide, titanium dioxide, also has 2DEC. So this discovery was very important. First, this these two materials can be easily deposited. So also widely used. Second, they can be deposited on any kind of substrate. Third, this sheet carrier density is very high compared to, well, it's higher than the LLSTO system. So all these advantages show this huge potential in device applications. Okay. So as we mentioned earlier, the heterostructure was deposited by ALD, and therefore these things are like amorphous or polycrystal. So this is a very interesting part of this system. This polycrystal oxide thing can still have a 2DEC. So the 2DEC system in ours, the new system, aluminum oxide and oxide, also had some similarity to the LLSTO system. First, its carrier density can be controlled by this aluminum oxide overlay. So the resistance, this is a figure of resistance as function of thickness. The resistance drops at this critical thickness. It's about 2.5 nanometer. So at when the sample, this aluminum oxide thickness is larger than that, we start to get the carrier density by Hall effect. So you can see the carrier density actually has the maximum when the thickness of an overlay is 5.5 nanometer. So the carrier is slightly higher than the LLSTO case. Another interesting phenomena for this system is that the 2DEC can also be controlled by the titanium dioxide button layer. So there's a critical thickness for this titanium oxide button layer. It's around like 6 nanometer. When titanium oxide layer is thicker than that, you can also have 2DEC. So to control the 2DEC property, it's key to understand the origin of the 2DEC formation in this system. For LLSTO, it's believed that 2DEC is associated with this polar discontinuity at the interface. But this shouldn't be the origin of aluminum oxide, titanium dioxide, because they are polycrystal. So one idea is that during the ALD growth, there are some, let's say maybe side effect. So this oxygen vacancy could form due to this reduction process. So because of that, some titanium 4 plus actually become 3 plus, providing additional electron at the interface. So our goal is to use the RIXS to study all these like 3 plus and 4 plus features to understand its electronic structure. So okay, this slide is about RIXS. We are using RIXS as a tool to study our system. And this very simple idea is RIXS is photon in, photon out technique. It has a lot of advantages, as you can see here. Just one thing I want to emphasize, RIXS using this resonance effect to kind of enhance specific electronic contributions, and also it has this selectivity on elements at a specific absorption edge. So in a typical RIXS spectra, there are a lot of different contributions. Like this, you see phonons, you see meganon, DD excitations, charge transfers. So we will discuss more details on the titanium LH RIXS. So this is titanium L3H. It's a transition from 2p3 half to 3D. So this, as you can see here already, there are a lot of channels and it's quite complicated. So how do we distinguish that? So a typical trick for these people is we just vary the instant energy or like excitation energy and see how these contributions evolve. Then we can tell them. So let's roughly look at these transitions. For titanium 4 plus, the electron configuration is D0. So there's no electron in D levels. So now there's one electron to be excited to the D level, and then it goes back. So this transition, it goes back and emit the exact same energy. So the transition is called the elastic emission. So there's no loss. But for some electrons, they have this energy loss due to the electron phonon coupling of this crystal. Then it's called LEL features. So it's due to the electron phonon coupling. And if we take this oxygen 2p into consideration for 4 plus features, then there are 2 additional channels. One is charge transfer, the transition between these 2 bands. And there's another one is called this 2p fluorescence. It's a transition between the localized, delocalized states. So these are 4 possible feature contributions for this 4 plus. And I would like to emphasize that for this LEL and the charge transfer, the transition is fixed energy. So the loss is also fixed. That means no matter what the energy we use, the peak position should be the same. And then let's look at 3 plus. For 3 plus, there's one electron at this T2G level. So if we do this T2G resonance, so the electron goes up, then it will come back. So it's still elastic excitation. But if we do this EG excitation, the electron goes up, then there are 2 possible channels. These are additional channels. So there could be this transfer between D2D levels. It's called the DD excitation. Then there's another, a second transition is some delocalized state. They could have transition between the D levels. So so these are the for 3 plus, and note that for this titanium dioxide, the valence state for titanium is 4 plus. The Bach property is 4 plus. So the titanium 3 plus ions, they are located at the interface, and it's believed that this titanium 3 plus leads to 2DEC formation. Therefore, using RIXS, we can pop these 3+ features, contributions, and the starting is electronic excitation. So another emphasis is this LEL, these features. It's supposed to be related from the back part, but we will see in our system, very interesting, it's related to the interface as well. So let's get into the experimental result. So this the left figure is the X-ray absorption data. So the vertical axis is the excitation energy. Y-axis is absorption intensity. So there are two main contributions, two main peak here. One is T2G, the other is EG. So you can see a lot of cuts here, starting from the T2G. It's called like A cut, B cut to O cut. It covers all these transitions. So at each cut, we have one RIXS spectrum. This is a combination of all these parts from A point to O point. So you see a lot of things going on, a lot of transitions. So let's look at it together. So at this like a huge peak here, it's a contribution from elastic emission and also LEL. And then between 1 and 4 EP, there are like as a T2G, there's no peaks. But when it goes to this EG excitation, you start to see a peak coming out. And then when you change the energy, then you see this splitting. There are two peaks. So this is a typical feature for titanium 3+. And then also at T2G, you also see this charge transfer and fluorescence, they are like mixing together. But then when you do this energy moving to higher excitation, then you see this charge transfer and also 2p split out. So that from here, we already can determine a lot of contributions. And then in the rest of this talk, we are gonna focus on this 3+ feature and also the elastic plus LEL, because these are all related to the 2-deck. Okay, so this is a RIXS map coming from 3 different samples. So the difference is titanium dioxide bottom layer. It goes from 2.8 to 20 nanometer. So this RIXS map is measured around this EG excitations. So you can see that for all these samples, it has this very strong elastic peak. And then there's a small bump for 3 samples. This small bump is related to the LEL. And then there's a V-shape, these features. It's related to titanium 3+. So now we see that all these samples has these interesting features about 3+ and the LEL. So we will look into it. So first we look at the LEL features. So in order to like distinguish this small LEL feature from the elastic, we do some analyze. We sum all this spectrum here for one sample. So then we put all these different thickness of samples together. So if this peak, zero energy loss peak, is really elastic peak, then it should be a Gaussian peak. So you can see this gray square color one is an elastic peak, and our heterostructure samples has small tails. If the titanium oxide is thicker, then the tail is getting stronger. So this is very nice evidence for this electron phonon coupling. So for this electron phonon coupling, we can learn how to analyze it from the literature. So here for this titanium dioxide back sample, they also see these small tails. And for this small tail, it can be actually fit by the multiple phonon peaks. So there are 2 constraints. The first constraint is this peak position has to satisfy this quantum number, but times phonon energy. And then the second constraint is the intensity ratio between the peaks should be constant. It satisfies this equation. And also from this equation, because we determine this ratio by fitting, and then we can determine this electron phonon coupling energy. So for our system, we add 4 phonon peaks to fit this LEL feature. And then we actually can get the information of electron phonon coupling. For our heterostructure system, the coupling energy is 122. It's slightly smaller compared to the back titanium dioxide. So the slight difference might be due to this interface effect for this heterostructure. And then the next part is this 3+ features. So we can see there are 2 kinds of components here. One is, so these 3 spectrons are measured at a different excitation energy. So you see one kind of feature, it has this linear shift from the D1 fluorescence. And then there's another contribution, this like 3 different DD excitation. They don't move when we change the excitation energy. So these are very interesting parts. So some are the delocalized part. So for the fluorescence, because the energy moves, so we know that that means that its energy level is kind of quite free. It's like free electrons. So we usually say, okay, this state is more delocalized compared to this DD excitations. And interestingly, people also found this very similar behavior to the LLSTO system. So we see all these similar part between these systems. And then we learned that this titanium 3+ and LEL features, they exist on all these heterostructure samples. We also want to know these 3+ are whether they are from the back or the like interface. So we do a trick. We divide the RIXS intensity by the titanium dioxide thickness. So it's like a step of normalization that represents this RIXS intensity per titanium atom. So if the titanium 3+ RIXS peaks uniformly distribute in the same bin, that means the relative RIXS intensity should be 1, no matter the sample thickness is. So, but we see that at the thinner sample, actually the relative RIXS intensity is much stronger. So for the case of like 3+ DD and fluorescence, it's even like 8 times higher. That means this DD relative things, 3+ features, they are like strongly interface-like. That's a very strong evidence that they are related to that. And then let's come back, go to this LEL. For LEL, you can see it's supposed to be back property, but still, when the sample is thinner, you see there are some higher relative intensity. So that means the phonon peak is a little bit complicated. It's the combination of interface and also back contributions. So some electrons still contribute to that. Okay, so okay, it's very nice. We are almost on time. So this is a summary of my talk. So the take-home message of my talk is that we have done this restarting on this new heterostructure system, and then in these heterostructure samples, we see this very strong evidence of 3+ states. And we think these 3+ states are due to the like upstream vacancies. And we also find this in relative intensity for this interesting feature, like 3+ features, DD fluorescence. They are like strongly interface-like, and also the phonon part is also relative to the interface. So that means we can change the 2-deck property by controlling these parameters, which is very important for device applications. So okay, that's all for my talk. There are some future directions, and I don't know if maybe I stop here because it's already 20 minutes. And if you have questions, please any questions is welcome. Yeah. Okay.
Cheers. Yeah, thanks. That was a good talk. Some interesting research there. If anyone's got any questions, they can put them in the Q&A. Here we go. Yeah, there's one question already in the Q&A. This is from Dota. Says, I missed if you calcine the samples after ALD or if they are amorphous. So are your ALD samples amorphous?
Oh, so okay, right. For the sample, we find some interesting behavior. You can see when the sample is thinner, like 2 nanometer, the absorption looks different from the like 8 nanometer sample. That means actually the crystallization changes. So when the sample is thinner, it's actually amorphous. And then when the titanium dioxide becomes thicker, it transfer to polycrystal. So that's some interesting things. You could see that in our paper, actually, this one. So they have some discussions on that.
Okay, cheers.
Yeah,
right.
sorry.
Thanks a lot. Okay, so in that case, we'll move on to the next talk. Thanks a lot for that one. So it's interesting. So for the last talk of this session, it's going to be Victor Kimberg, who's from the KTH Royal Institute of Technology in Sweden, and he's going to tell us a little bit about the theory of RIXS this time. So yeah, if you want to go ahead and look forward to it.
Yeah, thank you very much for introduction. And yeah, I'm very thankful for organizers to picking up my talk. So now I bring you a little bit in different universe of soft phase, soft matter of gas phase and liquid molecules. So let's see what's happening here. And here you see the outline of my talk. So I start with a brief introduction of our theoretical approach, and I hope even experimentalists can pick up main ideas because they're quite simple. Then I would be talking about RIXS studies of isolated molecules and the gas phase measurement, and combining with experiment and what we can find out there. And at the second part, I will talk about liquids and actually what the high resolution RIXS measurement combined with the theory allowed to get from point of view of molecular properties and so on. Okay, so the first step in all theory, whatever subject you have, of course, would be the electronic structure calculation. And in particular, in the X-ray spectroscopy, it's, of course, we're talking about a very special state of matter, which we call the core excited state, when we promote the core electron to some unoccupied valence orbital. And here, the simple methods would not work because they just collapse to the ground state. And for this, we use actually a set of different methods of different level of complexity, let's say, starting from very basic Z+1 approach, which actually was in use quite a lot in previous decades, let's say, but still until now we use it very much actually for some kind of estimation and so on. So this method is very simple and straightforward. So basically, idea is that the core electron is localized so close to the nuclei so that basically leaving from there, the rest of the molecule would see it as their another next atom in a periodic table. So basically carbon is substituted by nitrogen and so on. And then we get quite actually good estimate, let's say, not accurate, but for a good estimate for a core excited. Then it could be more complex approach, still using Hartree-Fock method with relaxed and frozen orbitals. And of course, in our business, we mainly use a configuration interaction approach when we, also here is different, let's say, types of it, which is shown here. And this method is giving really good results in terms of accuracy and so on, yet it's quite challenging to compute for the system bigger than, let's say, a few atoms. So then now we quite a lot using of density functional theory for computing this. So as soon as we solve the electronic structure of a molecule or liquid, I would talk about liquid a bit later. We can scan actually the electronic energy by changing the coordinate of atoms. And then we can obtain what we call the potential energy curves in one-dimensional case of potential energy surfaces. And then using this, we actually can solve our next step when we are doing the vibrational dynamics or nuclear dynamics in the system, which is triggered by X-ray radiation. So to compute this, we basically can have a two equivalent or alternative approach in energy domain. So it's described, the scattering amplitude would be described by the well-known kind of Kramers-Heisenberg type of equation. As you can see, it's written here. So it's the meaning is quite simple. So basically here you have Frank quantum factors from the ground to core-excited state, and then from core-excited to particular final state, and the resonant denominator. So then summing it up, you get a RIXS spectrum. So actually exactly the same thing can be formulated in time domain. And here we compute a spectrum as autocorrelation function of the object, which we called the wave packet. This is time-dependent coherent superposition of different vibrational states in the molecule. And this time-dependent approach is actually very good for computing and different processes, which shows very fast and non-trivial nuclear dynamics. However, it's quite expensive as compared to energy domain. And for this, we suggest, and we use basically now in our calculation, so-called the mix representation, where we use a time-dependent representation for a particular bonds or nuclear coordinates, which exhibit the very fast nuclear dynamics, and the rest of the system can be explained as stationary. So then for this, we have a Hamiltonian, which is a sum of two parts, time-dependent and time-independent. And through this, I would not go through this derivation here, but the final equation for RIXS cross-section, you can see, indeed, it's like the combination of these Frank quantum factors, as we see in the previous slide for energy domain, and the time-dependent wave packet for the vibrational modes, which we consider with a time-dependent approach. So here you can see a typical RIXS from isolated molecule, and probably, there's also soft X-ray range. Here is the example of water molecule. So we core-excited to first valence excited state, which is dissociative in gas phase, and then we see decay either back to the ground state, which we called the quasi-elastic band. It is here. So energy loss is incident minus emitted, as in all other RIXS measurements. And why it's quasi-elastic? Because it's basically it's elastic in terms of electronic excitation. However, due to fact that vibrational excitation is obtained due to the dynamics in the core-excited state, it's inelastic in terms of vibrational state. And here we have, the rest of the valence excited state, which is reflected in RIXS. And today, since, I have quite a short time, so I would actually focus myself in all examples I show today would be focused on the quasi-elastic band. So basically become up to some core excited state and then go down back to the ground electronic state, gaining yet some vibrational dynamics. And so I hope I will show you that even this simple process like quasi-elastic RIXS allows to get a lot of information about different systems. So let's start with the water. And here you can see absorption spectrum of water molecule. So we take one s electron and put it on different virtual orbitals. So here you can see 3 first core excited states of water, and basically this electronic structure. And this is a sketch of the nuclear structure of water molecule. And here actually our mixed approach is working very well, because the stretching mode of two stretching mode of the water, symmetric and antisymmetric, they are very much coupled. So we use a 2D time-dependent approach for this type of measurements. And for the bending modes, actually we can use the stationary approximation, because actually it's bound and we don't need really to consider very much the fast dynamics here. So here you see the experimental RIXS spectrum. And okay, already some insight can be understood from these things. So we see that actually vibrational structure is so much different in the case of higher excited state, but yet also in these two, even naively we can see that it's kind of same peak. We see that it's some little shift happening. And actually there's a lot of physics behind this little shift. And this physics actually is coming from the way of the core excited wave packet motion, which is simulated here on this plot for 2 core excited states. So this lowest one, and this is the second excited. And we see that actually the dynamics of the core excited wave packet is totally different in these 2 states. So then actually the RIXS spectrum would be computed, and the projection of the time integrated wave packet in the core excited state back to the ground state. And then of course we can have all different intensity for different vibrational states in the back to the ground state, right? So here it would be important for the second part. So I show you here that it's in quantum system we see this Schrödinger cut dissociation. So basically we cannot distinguish which bond is dissociating. So in quantum world it goes along 2 simultaneously. So then using this approach, actually we can compute our theoretical spectrum, and it's shown here together with the experiment. And it's a very fantastic outcome actually from here, that just by tuning the excitation energy to different electronic core excited state, we can actually choose what kind of vibration we will pump in this molecule. So when we go to B1 state, for example, we only excite bending modes. So the molecule just start to bend without inducing stretch. And for example, when we go to 4A1 state, we induce only symmetric stretching. And in the case of middle state to B2, the pure symmetric stretching mode would be fully suppressed. So we call it like a concept of vibrational gating effect. So we can go through different gates to get a different type of excitations. And actually, this effect was already used a lot for actually obtaining the cuts through the potential energy curves in different systems. Okay, now let's go for a more complicated case like liquids. And basically we try to use a similar approach, which gives quite accurate results, even for the water like a liquid water. So it was our first attempt, which was published 2 years ago. And here actually we consider an ensemble of water molecule where we pick up just one side to make a RIXS spectrum and basically produce all dynamics of this molecule with keeping the all surrounding frozen. Then, since we don't know actually which molecule would be excited in this cluster, which we compute using the ab initio molecular dynamics simulation, then we have to compute this RIXS spectra for each molecule in the cluster. And then we do the superposition of this spectrum. So that's quite challenging approach, but I will show that it gives actually quite good results. So here we have a comparison, gas phase, liquid phase, and theory and experiment. So basically it's quite a good, I think, qualitative agreement between theory and experiment. And also it's like very good, on the first side, it's very good agreement between actually liquid phase and gas phase. So everybody can say, okay, it's kind of same progression we see here. And naively, we can say, okay, this is the same thing as we see in the gas phase when we excite to the first core excited state. So it just simply symmetric stretching mode of OH bond in the water molecule. However, situation in liquid is not so simple because indeed the hydrogen bonds that start to be formed, and how this bond affect the RIXS spectrum is actually very much dependent on the molecules around it. So some molecules, which we call a double donor, so they can create a double hydrogen bond. Some molecules create single hydrogen bond, and of course the strength of this bond also depends on the oxygen-oxygen distance and so on. So then actually this Schrödinger cat type of dissociation, which I showed you and paid you attention in the gas phase, is totally broken in the present case. So here you see the typical wave packet dynamics, and it's not symmetric anymore. So it's basically, we can really know where the molecule would dissociate depending on the hydrogen bond formation. So through this, actually the potentials would also modify. So here it's shown two cases. So the case R1, which shows a shallow potential. This is the case of the strong hydrogen bond formation, and the red potential is looks very similar to the gas phase. So actually it showed the broken hydrogen bond or no hydrogen bond. And here actually, because this potential are so different, the spectrum has actually no direct correspondence between peak number and quantum number. So it's already, you can see that starting from peak number one, we already have a 2 contribution for the green spectrum. So this idea we utilize to reconstruct, to actually use our theory to reconstruct the potential energy curves directly from the experimental RIXS using the genetic algorithm here. So we basically try to populate some particular bands in the RIXS spectrum using the different fitness criterion. So we use a weak or no hydrogen bond when we primarily have one vibrational state for each peak, similarly to the gas phase. And we have strong hydrogen bond when we can have a different kind of constraint when we have one or two peak for, the quantum vibrational state for each peak. Then using this criterion actually directly from the experimental results, we can extract the distribution of OH potentials depending on the, let's say, strength of the hydrogen bond. So this is a set of potential with the weak or no hydrogen bond, and this set of potential with a strong hydrogen bond, and this is a full set of the molecular potentials. So I still have a few minutes, and here is our most recent example, still the liquid phase, but now we come to the a little bit more complicated system, which is acetic acid in its liquid form. It's more complicated because we still are working on oxygen KH, but here we have two inequivalent oxygens, so the OC coupled to the carbon and OH, which is here on OH group. And here you can see the comparison of X-ray absorption spectrum. So the first peak is assigned to excitation of OC, and then the second peak is assigned to excitation of OH. And here is spectrum for liquid phase. And basically similar to the in case of water, we can say, okay, it's some little shift here and there, but basically the spectra looks very much similar. However, when we come to RIXS, we see the drastic difference in these two spectra. So this is a case of water, gas phase liquid, the case of acetic acid on the OC side, and the case of acetic acid on the OH side. And here is, you see tremendous difference between the gas phase and liquid phase. And actually in liquid phase, the vibrational progression is totally quenched. Why it's happening so? And actually this is a fact when RIXS show really its powerful and beauty abilities to do things. Actually, our ab initio calculations show here that indeed, if we compare the second peak in the gas phase, we have two states, sigma and pi, which contributes here. But for dimer, this sigma state fully disappeared here, and we have only pi state. So what is the physical picture of this? So we have sigma state, which is undependent state. So the molecules start to dissociate in the gas phase, we propagate far, and we have this long vibrational progression. Similarly, I showed you in the water. And in liquid phase, and sigma state is shift away. So it's basically moved into the higher energy. We see only excitation to pi star, which has no vibrational progression. So basically it's stuck here. So this dramatic change in the RIXS, it's kind of interesting feature, but could we find also some practical application of this? And we try to actually use it to understand a little bit more about the structure of local structure of liquid acetic acid. So this is our simulation, and also a lot of simulation from literature gives a different prediction on the liquid structure of acetic acid. So basically, it's conclusion that they combine in some kind of molecular chain. However, it's not really known how long this chain could be, or how if they form this cycle dimer structure, or yeah, what's going on. So here, actually, we can use our results in RIXS, and the idea is very simple. So we have, for example, this kind of chain shown here, and this end group of this range or this chain would give a very long vibrational progression for OH mode, because they behave very similar to the isolated acetic acid. So we expect here a strong vibrational progression, but this inside group, as a hydrogen bond is formed and sigma antibonded state is moved away, we should see no vibrational progression. So basically, from these, we can estimate the number of these end groups, or from another side, we can estimate the length of this chain. Basically, just comparing the place here, where we expect the first OH vibrational peak, to the noise level of the experimental RIXS spectrum. So I would not bother you with all these details of calculation, but then at the end, we came to the conclusion that the effective length of the acetic acid liquid is more than or about 3.5 molecule per this chain. Okay, so now I come to the summary, and I hope I give you some ideas that really high resolution experiments where we can see the vibrational progression, which also combined with high level ab initio simulation allows to really study the much details of local structure and dynamics in molecules. And even the very simple scattering channel, but back to the ground state allows to get very interesting insights. So in the gas phase, we see the gating effect and also control with the frequency detuning, with the molecular vibration and ultra-fast dissociation and multimodal dynamics. In the liquid phase, we were able to reconstruct some confidential interval for the potential and also get some understanding related to the hydrogen bond network formation and water and acid. And here is people participated in theory and experiment development, which I'm very grateful. And also, I'm very grateful for your attention. And I will be happy to answer a few questions. Thank you very much.
Okay, cheers. Thanks a lot. It was a good talk. Once again, if there's any questions, just drop them in the question and answer section. Doesn't appear to be any at the minute, so I'm just going to go in with one first of all. In the part of your talk where you're looking at the water, the liquid water, and you had to perform separate calculations for all of your individual water molecules in their different environments in order to build up the I guess the full picture of it. You mentioned, of course, that was quite time consuming to do. Approximately how many environments would you need to calculate this for to obtain something that converged towards the result you were looking for?
Yeah, so basically we do calculation for 64 molecules cluster in the box with the periodic boundary condition. So we also tried to increase it twice, the number of molecules, and we get quite, let's say, similar results. So probably, surprisingly, let's say it's not so big ensemble is needed.
So that's pretty good. And I guess, yeah, you can take that on with a pretty good level of theory then, in that case, if it's not so many to do.
It's very also simple system in a way. I mean, we have, of course, many different types of configuration for this cluster, but yeah.
Of course, yeah. Okay, that's good.
I have a question, and I'll use panel privilege to turn off my microphone and ask it. So a lot of the systems you've looked at are kind of hydrogen motions, and obviously that's related to the core whole lifetime. How far can you extend to other atomic motions, do you think? Could you get up to vibrationally resolved oxygen, nitrogen, or larger?
Okay, so here really what I show it's more or less everything related to H bond, and there is a particular reason to this because we have a quite a fast dissociation on this mode, so it increases a lot of dynamics in the motion. But in principle, so it's also possible to see in, let's say, O2 molecule or something when we go to N2 or NO and so on. I'm just taking the atomic numbers. Anyway, the lifetime is enough to see some sufficient, let's say, geometry change or elongation of the bond. On the soft X-ray range, we're talking about, let's say, 10 femtosecond time. So it's basically time of vibrational period. So it's enough. Yeah.
Okay, thanks very much.
Okay, and yeah, we've just got one hand raised from Dorota. If you want to, I think you should get to use the mic now.
Yes.
If you want to ask a question.
Unmuted me. Thank you very much for a very nice talk. I was just wondering about if you could use transition metal acetate instead of acetic acid, or you could do the calculation here.
Yes, in principle, yes. It's why not? Yeah.
Yeah, very good. I will talk to you maybe offline. Then. Cool.
It's let's say a little bit more challenging, of course, for metals because you have other type of electronic structure, which is much more complicated. But so, for example, we cannot do it same way like we did for water, because here this would be very much challenging. But yes, maybe for the using this kind of tricks as we did for acetic acid, where we only consider dimer, which is basically enough to do to check our ideas. So it could be possible, I think.
Okay, very cool. Thank you.
Okay, well, yeah, seems a good time to puzzle that one out over the break. We've got a 15-minute break now for coffees, refreshments, and what on the break. Looks like most people are back, and yeah, you're suitably refreshed, beer in hand, and ready for this afternoon talks. So, taking it away with the first one, it's Francesco Tavani from. Let me see. You come from Sapienza, University of Rome. And tell us a little bit about RIXS with theoretical techniques. So take it away whenever you're ready.
So good afternoon to everyone. My name is Francesco Tavani. I'm a PhD student in the group of Professor Paolo D'Angelo at La Sapienza University in Rome, Italy. I really wanted to thank the organizers for this nice opportunity today to present some works the group and some results the group I work with has obtained concerning the use of XIS spectroscopy combined with multivariate and theoretical techniques to study the mechanisms of relatively fast organic chemical reactions in solution on the scales inferior to the seconds, comprised between the milliseconds and second time scales, and involving organic substrates. Now, as you may all know, chemical processes that are dynamic are widely studied through spectroscopic techniques that are laboratory based, such as ultraviolet visible, infrared, Raman, NMR, EPR, X-ray photoelectron spectroscopies, and so on. If compared to these more conventional techniques, XIS spectroscopy offers, however, unique advantages to follow chemical reactions, for example. For instance, through XIS, one may monitor at the same time structural and electronic properties of a given photoabsorber in an in situ experiment. So for instance, if we're having, for example, a redox reaction, one may track the evolution of the oxidation state of a given metal center through the succession of time-resolved XIS spectra, and I will provide some examples of this in the following slides. Secondly, multivariate curve resolution or MCR data decomposition techniques, as some nice presentations have mentioned before, are proving to be really powerful techniques for the rationalization of time-resolved XANES data. And finally, one may interpret the results also from the structural point of view through numerous codes based on diverse theoretical principles, such as full multiple scattering techniques, DFT or time-dependent DFT, BSE, the solution of the Bethe-Salpeter equations, core-hole equations of motion, and so on. So our group has focused the research on a specific system of chemical interest, which is that of non-heme iron complexes. Non-heme iron complexes are man-made catalysts that contain iron. An example of a typical non-heme iron complex is shown in this image in blue, where the iron 2 metal center is coordinated by 4 nitrogen pyridine ligands and by 2 solvent molecules. These catalysts mimic the natural reactivity of iron-containing enzymes such as mono and dioxygenases. And these are enzymes the cell has uses to catalyze the oxidation of notoriously strong bonds, such as carbon-hydrogen bonds. So the scope of the purpose of non-heme ion complexes is to mimic this reactivity, and understanding the mechanisms through which these catalysts act, and the structure, most importantly, of the intermediates formed during their activation and successive oxidation of the given substrate of interest may be very important towards a future more rational and optimized design of such, and improved design of such catalysts. So how do they work? The first step requires the activation of the catalyst. And this is achieved by the reaction with different possible terminal oxidants. So for example, peracetic acid, as shown here, or hydrogen peroxide. Upon addition, for example, of the non-heme complex shown in the slide with peracetic acid, an iron 4-oxo complex formed, and this species exhibits very short iron oxygen bond between 1.6 and 1.7 angstroms, and it is the real active species. So in the presence of a substrate, this will be the active species that oxidizes it. So a first study we performed involved simply the bimolecular reaction of the non-heme iron 2 complex shown in this slide with peracetic acid. So we're looking only at the activation of the catalyst. And we performed this through a time-resolved XAS experiment at room temperature. Now, at room temperature, this reaction is over in a second. So clearly, in order to unveil the intermediates involved, one needs to use an energy dispersive XAS setup. And this was enabled by performing the experiments at the ID24 beamline at the European Synchrotron radiation facility, leveraging also a stop flow apparatus that in order to mix the solutions containing the two reactants, and the stop flow apparatus had been previously used at the beamline for some very nice XAS time resolved experiments involving reactions on the second to minute timescales. So in this slide, we're looking at the iron K edge of the initial pristine, let's say, iron 2 non-heme complex at T equals 0. Upon addition of peracetic acid by means of the stop flow, after 40 milliseconds, one may clearly see an edge shift towards higher energies, and this is associated to the formation of an iron 3 intermediate. The reaction proceeds and the spectra continue to move to higher energies until after 200 milliseconds, the iron 4 oxo intermediate true active species forms. And this experiment was performed in the absence of a substrate. So in the absence of a substrate, the iron 4 oxo decays to iron 3, which represents in a dimeric form, represents the reaction product. At this point, one may interpret the experimental data through MCR. Basically, the decomposition takes place by writing the data matrix mu containing the experimental XANES time-resolved spectra on each of its columns as the product of two matrices, S and C. And S contains the spectra of the certain number of key components that contribute to the measured signal, weighed by their fractional concentrations contained in matrix C. And one can determine the number of key components contributing to the XANES data through statistical tests. If that is done, the results indicate that there are 3 components contributing to the data, and the extracted spectral and concentration profiles are shown respectively in panels A and B in the image on the right. Now, the spectrum in blue, shown in panel A, the iron cage spectrum is associated to the initial iron 2 species. In fact, its concentration, as shown in panel B in blue, rapidly decays to 0. The spectrum in green, shown in panel A, is associated to an iron 3 intermediate. In fact, its main edge energy is slightly at higher energies if compared to that of the iron 2 initial species. One may note that, interestingly, its concentration increases in the first 80 milliseconds from reaction start and decreases almost to 0 for this following that, and then rapidly increases to constitute the main reaction product. Finally, the most interesting spectral component is the one in red, And this is associated to the iron 4 oxo formed intermediate. In fact, it exhibits, as you may see in the inset of panel A, a nice 1s 3D dipole forbidden transition. And this is due to the non-central symmetry of the iron 4 oxo complex, due to that very short iron 4 bond. And the concentration of this intermediate is maximum towards 200 milliseconds from reaction start, and then rapidly decays to 0. But our approach was sensitive enough to unveil its lifetime. One can obtain further insight into the structures of these intermediates by performing multiple scattering calculations in order to reproduce the data. And the results of this operation are shown in this image, where in each of the panel you have the blue dotted curves that represent the MCR extracted spectral components, while the red curves are the theoretical simulations performed on the basis of the optimized molecular clusters shown on the right of each panel. So overall, there is a quite good agreement, and this allows detailed quantitative characterization of the structures, for example, of the iron 3 peroxyl intermediate and of the iron 4 oxo intermediate. Now, moving forward, we then focused our attention to the true interesting step, which is the catalyst oxidation of a given substrate. Let's imagine we have already formed the iron 4 oxo species shown in this image, a slightly different catalyst, but the same principle. And the substrates that we investigated are those shown in this image, and they are thioanisols substituted differently in the para position. So a series of different thioanisols who react with the iron 4 oxo complex through a direct oxygen transfer reaction. They are oxidized, and the iron 4 oxo complex is reduced to iron 2. So again, the same approach, stop flow approach, was performed at the ID24 beamline. This time, coupled spectroscopic data was recorded, both XAS and contemporaneously ultraviolet visible data. And the results are shown of the XAS measurements are shown in this image. You may see on the top of the slide the results concerning the oxidation of the paramethoxy thioanisole derivative. In the center of the slide, those concerning the oxidation of simple thioanisole, and in the bottom of the slide, those concerning the oxidation reaction of the parashano derivative. Now, panels A, C, and E present selected iron K edge spectra at selected time intervals from reaction start for each of the investigated processes. As you may see, there are arrows indicating the evolution of the spectra in time. They consistently all move to lower energies as the reactions proceed. And this is expected due to the fact that we're looking at the reduction of the iron 4 activated catalyst to iron 2. Conversely, panels B, D, and F present the evolution of the edge energy of the spectra as a function of time. And you may see that this relationship is exponentially decaying. And not only that, the kinetic constant that regulates this decay differs depending on the nature of the substrate. So the reaction is over quicker for the paramethoxy oxidation, and it's much slower if, when one is considering the oxidation of the parashano derivative. And this reflects nicely the different electrophilicity of these substrates. Further, one may extract the kinetic pseudo first order constants from these curves. And these are in perfect agreement with those already measured for these reactions and present in the literature, thereby providing an evidence that XAS may be fruitfully employed to extract kinetic information for bimolecular reactions occurring in solution with timescales that are inferior to the seconds, on the millisecond to second timescales. At this point, one may take a closer look at the coupled, as I mentioned before, ultraviolet visible data for the reactions involving the oxidation of the paramethoxy derivative and the parashano, the paramethoxy derivative on the right and the parashano derivative on the left. As I said, the data were collected in an orthogonal fashion where the chamber is evidenced in green here, and at 90 degrees, the ultraviolet visible spectrum were recorded if compared to the beam if compared to the X-ray B. Now, panel A on the left presents the ultraviolet visible data for the oxidation of the para channel substrate. As you may see, it consists mainly of a single broad peak centered at 695 nanometers that disappears in time. Time is the x-axis. So this peak is due to the iron 4 oxo initial species that decays and converts to iron 2. Conversely, in panel B on the right, one may see two curves, a red curve and a blue curve. The red curve is the intensity evolution measured at a wavelength of 695 nanometers, while the blue curve is the evolution, the same intensity evolution measured at 513 nanometers. And this is due to the increase of iron 2. You may see that the rate of decrease and increase of the red and blue curves are the same. And this strongly suggests the direct conversion of iron 4 to iron 2 in this reaction with no intermediate involved. This does not happen in the case of the paramethoxy oxidation. As you may see in panel B on the bottom, the rate of decay measured at 695 nanometers is much sharper and quicker than the corresponding increase at 513 nanometers. And this evidence, together with the fact that an isosbestic point, that is a point where all the spectra intersect, is not visible in the data. These evidences strongly suggest that there is an intermediate species forming between the iron 4 initial reactant and the iron 2 product. One may perform statistical tests on these data to confirm this hypothesis, and this has been done, but for brevity, I will not present those results. At this point, if we only focus on the paramethoxy, the oxidation of the paramethoxy derivative, there are three components constituting the coupled data. And one may perform the MCR decomposition of the coupled ultraviolet visible and XAS data. And the results of this are shown in this slide, where panels A and C present the spectral profiles for the three components for the ultraviolet visible data and for the XAS data respectively, while panels B and D present the associated concentration profiles. One may see that there is the initial iron 4 species shown in red in all panels, the product, which is iron 2, and the intermediate in green is assigned to an iron 3 species. This may be confirmed, for example, looking at the XAS extracted component for the iron 3 intermediate shown in panel C. In the inset, you may see that all species exhibit a 1s3d transition, and the energy of this transition for the iron 3 intermediate is right in between those of the iron 4 and iron 2 intermediates. This evidence, together with structural calculations, always full multiple scattering calculations that nicely reproduce the data, give us a strong suggestion that iron 3 is forming in this reaction, and its concentration profiles follows the trends shown, for example, in panel D, where there is a maximum concentration of 500 milliseconds from reaction start of the species, and it decays, and after 1.5 seconds, it is no longer present. So our approach enabled the detection of a significantly labile intermediate species. At this point, finally, we changed the nature of the substrate. So now we're looking at a different class of substrates, carbon-hydrogen bond containing substrates. On the left, you have DHA, that stands for dihydroanthracene, and on the right, diphenylmethane. And these two substrates react again with the same iron 4 oxo activated species, and they're oxidized, and the iron 4 oxo is reduced, at least in partly, to iron 2. So the same technique was used. So coupled ultraviolet visible XAS data were recorded. And here we're looking at the XAS reaction data. So I would like to focus your attention on the two-dimensional plots shown in the slide. On the left, we have the XAS two-dimensional plots for the DHA reaction. On the right, those for the diphenylmethane oxidation. So the x-axis constitute the energy. Y-axis is the time from reaction start that increases going upward. And you may see dotted constant energy cuts in white for each panel. And these are the energies of the maximum of the first reaction spectra from reaction start that serve as a reference. while the blue traces in each panel represent the evolution of the maxima of the XAS spectra as the reaction proceeds. So you may see clearly that the maxima of the spectra deviate from the energy positions of the initial spectrum. And this is expected due to the reduction of iron 4 to iron 2 in both reactions. Somewhat, this reduction is quicker in the case of DHA. The deviation is very quick from the energy of the initial maximum. Whereas in the case of the oxidation of diphenyl methane, it's somewhat slowed down. So this evidence, the fact that it moves, this blue curve moves to lower energies less sharply than that of DHA, suggests in a qualitative way, of course, that there may be an iron 3 intermediate formed whose effect would be to slow down the decay to lower energies of the blue curve. If one analyzes in depth the ultraviolet visible data and performs the same statistical tests I mentioned earlier, this picture is confirmed. And the results are those presented in this slide. In the case of the oxidation of DHA, we have two components contributing to the data, iron 4 in red and iron 2, and panel A presents their ultraviolet visible spectra. Panel B, their fractional concentration evolution, perfectly symmetric as expected in this case. And panel C, the extracted xane spectra for these two same species, exhibiting the same nice 1s3d transition in red in the case of the iron 4 oxo species. So in this case, the iron 4 oxo complex oxidizes DHA to dehydroanthracene and forming iron 2 as a product, and the iron 3 intermediate that is expected by the literature for this reaction does not accumulate at all. And it keeps a very, very low concentration, and we cannot detect it in our conditions. Conversely, in the case of the oxidation of diphenyl methane, three components are present, and they are the exact same components for the previous three-component reaction I have shown previously. And one may look at the concentration of the iron 3 intermediate in green. Again, it reaches a maximum concentration, as you may see in panels B and D, towards 90 seconds from reaction start, and it decays rather slowly, and it is still present at the end of the reaction, and this may be independently verified by tests on the reaction mixture once the process is completed. So in this case, our mechanistic hypothesis is shown in this scheme, and the iron 4 oxo species oxidizes diphenyl methane. And the iron 3 intermediate forms at a much slower rate, and it accumulates and only partly converts to the iron 2 end product. So with this, I have concluded my presentation. So summing up, a method to obtain structural mechanistic insights into bimolecular reactions occurring in solution that involve organic substrates and occur on the second to millisecond timescales has been benchmarked, and structural insights have been obtained for the intermediate species that are formed regarding iron complex reactivity, and this may improve their future rational design. This work cannot have been performed without the very fruitful and nice collaboration between many research groups, specifically those of Professor Osvaldo Lanzalunga and Stefano Di Stefano at La Sapienza University. Giorgio Gabugasa and Francesco Gabugasa, who also work on the project at La Sapienza University, Dr. Andrea Martini, who collaborated from the University of Torino, who collaborated specifically on the application of the MCR technique, and Dr. Sakura Pascarelli and Manuel Monte, who were present at the ID24 beamline measurements. And of course, huge credit to my professor and supervisor, Professor Paola D'Angelo, who led the research, and thank you for your very kind invitation and attention.
Okay, cheers, Francesco. Another good talk. Have we got any questions from anyone? No, nothing in the chat so far. So I'll just go ahead and ask one here. So I come from a theoretical perspective, so not so much from the same angle here, but certainly from a theoretical perspective, in these kind of solutions where you've got these sort of multi-component processes going on, it can be quite difficult to sort of conclusively identify specific pathways when there might be multiple ones. So in your case, do you only see these three potential, or at least in the case of the intermediate, the three potential complexes, or do you have to strip out signal from all kinds of other bits in solution or other pathways, or is it just a case that there are only these ones?
Well, indeed, yes. I mean, one can perform numerous statistical tests on the data and on the coupled data. So, for example, independently on the ultraviolet visible and CONEXS data, which is what we have done. And these there are a number of these tests that one can perform. They're basically based on principal component analysis. And one can pretty reliably estimate the number of components that are present that contribute to the data mixture, basically due to the Lambert-Beer law that one is always assuming it holds. And as for the nature of these components, so the number is pretty reliable. The nature of these components, the MCR technique suffers from a certain degree of rotational ambiguity. So the decomposition is not unique, but the fact that the use, let's say its application to two independent techniques, and the fact that these, for example, the Xane spectra may be reproduced by calculations, really strengthen the reliability of the assignments that one has made.
Cheers. Yeah, no, that's very clear. Yeah, perfect. Thanks a lot.
Thank you.
So that said, we're moving on to the last talk of this session, which is also the second talk. A pretty interesting talk. I think it's it's a topic that's close to my heart. From my own work, we're looking at trying to predict the form of Xane spectra with machine learning. So we're taking the structure and going towards the spectrum. But here, this talk, it really looks